Hello again. This is Math 2233 coming to you from the College U DuPage, and this lecture is entitled Vector Fields. As always, please be an attentive listener as you watch this video. In this chapter, we're going to study the calculus of vector fields. These are functions that assign vectors to points in space. So x, y, z, a point in three-dimensional space, is assigned a vector, capital F, which is a function in turn of x, y, and z. In particular, we're going to discuss line integrals, which can be used to find the work done by a force field in moving an object along a curve. And we're also going to talk about surface intervals, which can be used to find the rate of fluid flow across the surface. And the connection between these new types of integrals and the single, double, and triple integrals that we've already studied are given by higher level, higher dimension versions, I guess, of the fundamental theorem of calculus. And these are going to be Green's theorem, Stokes' theorem, and a thing called the divergence theorem. But we're going to start by studying vector fields. By way of introduction then, what we have down here are arrows, and the direction of the arrow shows the direction of the wind, and the length of the arrow shows the velocity of these vectors, and these are vector velocity fields, or velocity vector fields, in the San Francisco Bay area. And so you see at one point in time, this is going across, this is the Golden Gate Bridge here, and so you can see that's where the strongest winds are at that time. At another time in the day, the strongest winds are here, but you can see the directions and magnitudes of the winds everywhere. So this is an example of a velocity vector field, and that's a good central example to think of. Here's some other examples of velocity vector fields are shown here. This is difficult to see, but this is out on the ocean, the way the winds are. And here's an interesting example showing what happens with the velocity as we hit an airfoil, and this is like a wing on a plane. And it might not be easy to see, but the velocity on the top is greater than the velocity on the bottom because it has further to go. And we'll talk more about the consequences of that later. Another type of vector field is called a force field, and this is associated with a force vector at each point in a region. These can be electrical fields or magnetic fields or even gravitational field. And we're going to talk about the gravitational field specifically. Actually, I think we'll talk about the electric field as well. But in general, a vector field then is a function whose domain is a set of points in either R2 or R3, and whose range is a set of vectors in V2 or V3. And this definition says that. So if D is a set of points in R2, that's a plane region, a vector field on R2 is a function capital F that assigns to each point, x, y, and d, a two-dimensional vector, which is f of x, y. And here, that bold face means that is a vector. Now, the best way to picture a vector field is to draw the arrow representing the vector f of xy starting at the point xy. Now, it's impossible to draw all of these points, but we can get a good idea by picking a few representative ones. In general, then, f of xy is going to look like p of xy times I, the vector I, plus q of xy times j, and sometimes this will be written in I and j notation like in your physics courses, and other times it will be pointy bracket pq into pointy bracket like this. And sometimes, in short, you'll say f is equal to p times I plus q times j. And again, the bold face means those are vectors. Those are the I and j vectors that we've studied along the way. P and q are scalar functions, and those are the scalar fields to distinguish them from the vector fields. And this is an example of a vector field, or at least part of a vector field on R2. So at this point here, what happens is at that xy, you get this vector. At this point, you get this vector. At this point, you get this vector. This point, you get this vector. And this point, you get that vector. And there's something associated with each point within the region. Let's do a little example, and we're going to sketch the vector field, which is f of xy equals yi plus 1/2 j. Now this is a vector field in 2 dimensions, so we can draw the plane. Now you'll notice that whenever you take y to be 0, that is a point along the x-axis, what's going to happen is the y is going to be 0, and that means that f of xy is going to be 1/2 in the j direction. So you see these vectors, that's what's happening along the x-axis. All those vectors are the same length and everything else. Now beyond that, what you want to do is pick a representative set of points. And so this column, these are points x and y. So there's 0, 0, 0, 1, 0, 2, 0, minus 1, and 0, minus 2. But then we plug it in to the capital F of xy. Now these are going to be pointy brackets. So here I get pointy bracket 0, 1/2, pointy bracket 1, 1/2, pointy bracket 2, 1/2, pointy bracket minus 1, 1/2, and pointy bracket minus 2, 1/2. And here's some other points that I can pick. 1, minus 2, and so on and so forth down to 1, 2, and I get these pointy bracket things. So I have 10 vectors that I can plot. But I don't only need to know the components of the vector, I need to make the vector drawing that length. So the magnitude of this vector is going to be y squared plus 1/2 squared, which is 1/4. So this is going to be the magnitude of them. And so what I can do is I can graph these vectors with these arrows, and that is the picture that I get from these 10. If I graph a few more, I get this, and what happens is these are tangent vectors to parabolas that I can look at, and the length of each one of them is that. And so you see, you get a display that looks like this, and you can kind of see what's going on. So why don't you give one a try? So here we have a vector field on R2 that's defined by f of xy is minus yi plus xj. And I want you to sketch some of the vectors to get a feeling of what's going on. You know what to do. Let's see how you did. So again, what we're going to do is we're going to pick points xy, and we're going to see what vector is associated with them, and we're going to graph those vectors and with the links, and you see what happens is we get something that looks like this. Now if you look at this, what you can see is that this is really a circulation pattern that you're going in a clockwise, excuse me, a counterclockwise rotation about a point. So that is what this vector field represents in 2 dimensions. And again, there's a bigger picture of the same kind of thing. Now it appears that each arrow is tangent to a circle with center at the origin. And we can confirm this by taking the dot product of the position vector, which is xi plus yj. And notice that we're calling this vector x, and then we're calling it xi, and that can be a little confusing. That's supposed to be bold, though. And so we can think about this as being f of the vector x, which is xy. And that you want to be very careful about this notation. But if you take the dot product of x, which is that vector, with f of x, which is this vector, you're going to get 0. So that shows that it's perpendicular to position vector, and that means, if you think about it, that it is tangent to a circle with center at the origin, and it has radius of this. So notice that the magnitude of f of xy capital F of xy. The magnitude of that is the magnitude of the vector x. So the magnitude of the vector f of xy is equal to the radius of the circle. And again, it was circular motion. Okay, let's continue with our definitions. Now we're expanding things into 3 dimensions. So let E be a subset of R3. A vector field on R3 is a function f that assigns to each point in E a 3-dimensional vector f of x, y, z. Now this is a 3-dimensional vector. We're in 3-dimensional space. And so we have not only I, j, but we also have k, and these are functions of 3 variables, x, y, and z. And we could define continuity if capital F is continuous, if and only if the component functions p, q, and r are in fact continuous. And here's a picture of such a vector field. So at every different point in 3-dimensional space, we have a 3-dimensional vector. And again, sometimes we identify point x, y, and z with a vector. That's a bold vector, x, y, and z. Those are pointy brackets, and write f of x instead of f of x, y, z. So this becomes a function that assigns a vector f of x to a vector x. Now, some computer algebra systems are capable of plotting vector fields in 2 or 3 dimensions. This will do it in 3 dimensions, and these two certainly do it nicely in 2. And this gives you a better impression of the vector field than is possible by hand, because computers can do a lot of these kinds of things. And we do a computer plot of some 3-dimensional vector fields. Here is actually, no, these are all 2-dimensional here. We'll look at 3-dimensional. This is the circulation one that you did before. And you notice how the further you get out, the size of the vector grows. Here's a more complicated vector field. And here's one more complicated even than that, where we have, this is the capital F of xy. You might want to explore some of these. In fact, I would suggest that you do. And here's a problem. Sketch the vector field on R3 given by f of x, y, z is zk. Well, and I should have maybe asked you to plot this yourself, but this is a 3-dimensional thing, and we're able to draw this by hand because it's very simple. Most 3-dimensional vector fields are virtually impossible to sketch by hand, and you can use computer software to do it, but you do encounter them, and you are to be able to do calculations with them. And we'll look at some additional examples of these 3-dimensional vector fields later. These can be a velocity field or something like that. And in fact, here is this one, and you can see the way things swirl there. Here is this one, which is different than that. And here is this one, which is different yet again, and we're getting a slightly different view of this one as well. So you see, these things can be quite complicated, but also quite useful, because fluids are something that we are very interested in studying in biology as well as in physics. Okay, when would you use this? And remember that vector fields assign a vector to each point in a specified domain, and they can be interpreted by assigning a magnitude and a direction to any point in the domain. So physicists must consider the electrical force field generated by a charge. A vector field in 3 dimensions is used to model the force exerted by an electric charge at a particular point. Those are electrical fields and magnetic fields. Astronomers analyze the effects of gravity from multiple planets and stars at once. A gravitational field is a 3-dimensional vector field that shows the direction and strength of gravity acting at a point. And a third example here, the flow of air past an airfoil. Now that's like an airplane, but it's shaped like this in cross section, can be modeled with a two-dimensional vector field. Aeronautical engineers must design airfoils that provide sufficient lift for airplane wings to function correctly. This is kind of an amazing thing. There's a thing called Bernoulli's equation in physics that says that the pressure plus the density, that's the velocity squared over 2, is a constant for a given fluid flow. So you see we're hitting here, but in order for this to be a constant, that means that when we come here, the airflow, the fluid flow that goes across the top and across the bottom will meet again over here. But the top has further to go because this is curved, so it must go faster. And the faster the speed is, if you look at the equation, the faster the speed, the lower the pressure. So this has fast speed and low pressure. This has slower speed and high pressure, and that is called lift. And that's one of the reasons that airplanes can fly. And so that's what this is talking about. Let's look at another example. Imagine a fluid flowing steadily along a pipe, and let v of xy be the velocity vector at a point x, y, and z. Now, it's important that you realize that flowing steadily means that through each cross section a constant volume passes. So v assigns a vector to each point x, y, z in a certain domain E, the interior of the pipe, so that v is a vector field on R3 called the velocity field. And a possible velocity field is shown down here, and you see here it's going on. Now you may not be able to see this, but in this one the velocities are higher than they are over here. The vectors are longer than they are over here. It's also related to pressure, as we talked about before with the Bernoulli equation. But what really happens is you see the product of the area times the velocity is a constant here. So A1 times V1 is the same as A2 times V2. But if A2 is smaller, that means V2 is faster. And that changes the pressure on the outside as well. A very important example here. Velocity fields also occur in other areas of physics. For example, we got velocity fields and the counterclockwise rotation of a wheel. We saw that. And there are other examples that we also have previously looked at. And in fact, Newton's law of gravitation states that the magnitude of the gravitational force, this is showing the magnitude of F, is m. And these are two masses, small m and big M. Usually small m is going to be like a heavenly body, and m might be a person or a much smaller thing, times g divided by r squared. And this is Newton's famous inverse square law kind of thing, where r is the distance between the object and g is the gravitational constant. That's an inverse square law. I guess I already said that. Let's assume that the object with mass capital M is located at the origin. So I'm taking a big thing and sticking it at the origin. And we let this position object with mass m be at x, y, and z in three-dimensional space. Then r equals the magnitude of x, so r squared is equal to the magnitude of x squared. So the gravitational force exerted on the second object acts towards the origin, and the unit vector in this case is x over the magnitude of x. So f of x is equal to negative. You see it's going in towards the center. Up here we had the absolute value, so that was positive, but this is m, big M, g, over, this is now, since we were replacing this with that, we had r squared already, but then we were using a unit vector, so this is x over the magnitude of that, so that's why it ends up being cubed. Now, so this is, in fact, the force equation, and this is the vector equation that we're graphing over here. Now, physicists often use the notation x, the notation where you have X, Y, and Z representing the vector X equal pointing bracket X, Y, and Z. So they tend to use this. And if you write that in the I direction, you get this. The J direction, you get this. And the K direction, you get this. And this is the gravitational field that we have. So you see everything is being sucked into the big mass. And the closer you get, the stronger the attraction. And the same thing, a very similar thing is true with electrical charges. Q is located at the origin, and this is called Coulomb's law. Now it turns out this constant, which is called Coulomb's constant, there is a Coulomb's constant that's much bigger, but this is called Coulomb's law. And so this is what we get for our electrical force field. And you can see that there are strong similarities. And often to get the electrical field, not just the force field, you would divide this by Q because you would want to consider it as per Q. So if you do it by Q, the Q's would cancel out and you get an expression like this. So E is the electrical field on R3 called the electrical field on Q. Now the reason I wanted to bring this up is just to show you that what we're talking about has huge applications to electrical engineering, mechanical engineering, and physics in general. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.